Assume that matrix A is row equivalent to matrix B. Without calculations, list the rank of A and the dimension of the null space of matrix A. Then find basis for the column space of A, the row space of A, and the null space of A. So the first thing that we want to do here is find the rank of A and the dimension of the null space of A, trying to do this without calculations. So let's keep in mind here, we know that the rank of A, by definition, is equal to the dimension of the column space of matrix A, which is equal to the number of pivot columns. And we're lucky here, we are given a row equivalent matrix that is already in echelon form. We look up here at matrix B, this is in echelon form. So we can see the pivot columns. We can see we have a pivot column in the first column. We have a pivot column here in the third column and a pivot column in the fifth column. So the total number of pivot columns is 3. So you can say that therefore the rank of matrix A is equal to 3. Now we also want to do the same thing to find the dimension of the null space of matrix A. So let's think, what is the dimension of the null space of matrix A? Well, this is the number of free variables in the homogeneous equation. Or an alternative way to think about this is that this is the number of non-pivot columns. So if we look at our matrix A here, we have a 4 by 5 matrix. So there are 5 columns total. 3 of those columns are pivot columns, which means that therefore the dimension of the null space is 5 minus 3, leaving us with 2 non-pivot columns. And so we're ready now to go ahead and find the bases for the column space of A, the row space of A, and the null space of A. So let's get started with the column space of A. So I want you to begin by recalling that the pivot columns form a basis for the column space of matrix A. So looking up at the echelon form of matrix A, or in other words, matrix B, we can see that we have pivot columns in the first column, the third column, and the fifth column. So we can say that therefore a basis for the column space of A. And now, of course, we want to be careful. We use the echelon form to identify the pivot columns, but we need to use the columns of the original matrix A when defining the basis. So that means that our set B here, the basis for the column space, is the set of column vectors 1, 2, negative 2, negative 2, 4, 10, negative 17, 0, and last but not least, we have the column vector negative 3, negative 7, 15, 0. And so this is our basis for the column space of matrix A. So now let's go ahead and let's think about the row space of matrix A. And so again, let's begin by recalling that the non-zero rows of the matrix in echelon form, aka matrix B, forms a basis for the row space of matrix A. So the non-zero rows of the echelon form of the matrix, matrix B, form a basis for the row space of A. So again, looking at matrix B, the echelon form, we see that row 1, row 2, and row 3 are the non-zero rows. And so therefore, we can state that we have a basis for the row space of A, defined as set B, with the row vectors 1, 3, 4, negative 7, 3, 0, 0, 1, negative 1, negative 1. And last but not least, we have 0, 0, 0, 0, 1. So here, when we're defining the basis for the row space of matrix A, we're using the echelon form of the matrix to define these non-zero rows. And last but not least, we need to find a basis for the null space of A. So let's recall that the spanning set for the homogeneous equation matrix A times vector x equals a 0 vector forms a basis for the null space of A. So the spanning set of our homogeneous equation forms a basis for the null space of A. So in order to do this, we are going to need to continue row reducing matrix A to echelon form. So we can think of this as matrix A augmented with the 0 vector, which of course is equivalent to matrix B augmented with the 0 vector. And we're going to row reduce this to row reduced echelon form. All right, so we'll need plenty of room to find the basis for the null space of matrix A. So we know that we have the matrix in echelon form, matrix B, which is defined as 1, 0, 0, 0. We have 3, 0, 0, 0, 4, 1, 0, 0, negative 7, negative 1, 0, 0, and our last column, 3, negative 1, 1, 0. And we want to reduce this all the way to row reduced echelon form. So our first column is good, so we move to our second pivot position, and we'll use this to eliminate the entry above it. So we need to do negative 4 times the second row plus the first row to attain the new first row. So this will produce the equivalent matrix 1, 3, 0. Positive 4 plus 7 is negative 3. Positive 4 plus 3 is 7. And the second row still remains as 0, 0, 1, negative 1, negative 1. Third row is 0, 0, 0, 0, 1. And our fourth row is a row of all zeros. So our second pivot is good, and we move to our third and final pivot, and we want to use this to eliminate the entries above it. So we have two cases here. We'll need to do the third row plus the second row to attain the new second row, and we'll also need to do negative 7 times the third row plus the first row to attain that new first row. And so here we go. We are going to be left with the equivalent matrix 1, 3, 0, negative 3, 0. We then have 0, 0, 1, negative 1, 0, and 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. And so we have officially attained row reduced echelon form. And so this, of course, is equivalent to x sub 1 plus 3x sub 2 minus 3x sub 4 is equal to 0. We can see that our second row converts to x sub 3, or is equivalent to x sub 3 minus x sub 4 is equal to 0. We have that x sub 5 is equal to 0. And we'll make a love note here to ourselves that x sub 2 and x sub 4 are free. So to attain the spanning set, we need to find the general solution to the homogeneous equation, writing this in the parametric vector form. So we can take this equation, this linear equation, and write it in equivalent form one step further and say that x sub 1 here is equal to negative 3 times x sub 2 plus 3 times x sub 4. we have that x sub 3 is equal to x sub 4. And then we also have that x sub 5 is equal to 0. And again, we're making a note that x sub 2 and x sub 3 are x sub 2 and x sub 4 are free. So let's rewrite this in the parametric vector form. So we can say that our general solution for the homogeneous equation, matrix A times vector x, equals a 0 vector. So we have vector x is a vector in R5, x sub 1, x sub 2, x sub 3, x sub 4, x sub 5. So we have our first equation reads minus 3 x sub 2 plus 3 x sub 4. We then have x sub 2 is free. We have x sub 3 here is defined as x sub 4. We know that x sub 4 is free, and we know that 5 is equal to 0. So I'm going to incorporate a 0 into each row there. And of course, you can skip this step and go right for it. Otherwise, it can help to, again, incorporate zeros into those missing entry positions. So now when we separate this out, we can clearly see the vectors that span the set. So I have x sub 2 multiplied by the column vector negative 3, 1, 0, 0, 0. And we have plus x sub 4 multiplied by the column vector 3, 0, 1, 1, 0. And this, of course, we know that x sub 2 and x sub 3, x sub 2 and x sub 4 are free. They are real numbers, or any scalar we want. And so these column vectors here are the vectors that span the null space. And so we're ready to write our beautiful final answer here. We can say that, therefore, the basis for the null space of matrix A is defined as the set B with column vectors negative 3, 1, 0, 0, 0, and a column vector 3, 0, 1, 1, 0. And so this is our beautiful final answer in completing this question.